Picture the universe not as a collection of isolated stars and galaxies, but as a living, breathing network connected by rivers of invisible gas flowing through the emptiness of space. These vast currents, stretching millions of light years, are the unsung architects of cosmic history, shaping everything from the smallest star to the grandest galaxy. Yet, for something so fundamental, intergalactic gas remains one of the most overlooked forces in the cosmos. Today, we're pulling back the curtain on this hidden player, revealing how it silently orchestrates the birth of stars, the collapse of galaxies, and even the conditions that make life possible. Think of intergalactic gas as the cosmic glue holding the universe together, a primordial residue from the Big Bang, threading through the voids between galaxies like an invisible scaffold. Without it, the night sky would be a far emptier place. This gas isn't just leftover debris, it's the raw material for new stars, the fuel for galactic collisions, and the medium through which galaxies communicate across unfathomable distances. And here's the astonishing part. Despite its ghostly presence, it contains more mass than all the stars in the universe combined. So why don't we hear more about it? Because unlike blazing stars or swirling galaxies, intergalactic gas doesn't emit light. It's the universe's silent puppeteer, working behind the scenes. But modern telescopes and cutting-edge simulations are finally bringing its story to light. From the way it funnels into galaxies, sparking bursts of star formation, to how it redistributes heavy elements forged in supernova, this gas is the invisible hand guiding cosmic evolution. By the end of this journey, you'll never look at the night sky the same way again, because now you'll know the secret currents shaping it all. The cosmic web isn't just a poetic metaphor, it's the scaffolding of reality itself. Imagine tracing the universe with a highlighter, revealing a labyrinth of glowing threads where galaxies cluster like beads on a string. These filaments, stretching hundreds of millions of light years, are woven from the same intergalactic gas that flooded the cosmos after the Big Bang. But here's what's truly mind-bending. This gas isn't randomly scattered. It's organized into an intricate network shaped by the gravitational pull of dark matter, acting like an invisible blueprint for everything we see. Take the Great Wall of Galaxies, one of the largest known structures in the universe. It's not a solid wall at all, but a dense ribbon of intergalactic gas where thousands of galaxies have formed, drawn together by the gravitational currents of this hidden architecture. Without these rivers of gas, galaxies would drift apart like ships lost at sea, never colliding, never merging, and never triggering the bursts of star birth that light up the cosmos. And the gas doesn't just sit there, it's constantly in motion. Picture a cosmic conveyor belt funneling raw material from the voids into galaxy clusters, where it condenses into new stars. This is why some galaxies, like our Milky Way, are still alive with star formation today, while others, trapped in gas-poor regions of the web, have become cosmic graveyards, their stellar fires long extinguished. Even more astonishing, when galaxies collide, it's often the intergalactic gas between them that determines their fate, either sparking a fireworks show of new stars or leaving them starved and dormant. But the cosmic web's influence goes even deeper. It's a relic of the universe's infancy, a fossilized snapshot of the tiny density fluctuations that existed moments after the Big Bang. By studying its structure, astronomers can peer back in time, decoding how gravity amplified those faint wrinkles into the vast web we see today. It's like unrolling a cosmic scroll, revealing the story of how emptiness gave rise to everything. Yet for all its grandeur, the web remains elusive. Most of its gas is so diffuse, so achingly thin, that it's nearly invisible to telescopes. Only by observing the faint distortions it causes in the light of distant quasars, or by simulating its behavior in supercomputers, can we begin to map its hidden currents. And with every new discovery, we're reminded the universe isn't just a collection of objects. It's a dynamic, interconnected system, humming with invisible energy, and intergalactic gas is the thread stitching it all together. To understand the origins of intergalactic gas, we have to rewind the clock nearly 14 billion years back to the universe's first breath. In the fiery aftermath of the Big Bang, the cosmos wasn't filled with galaxies or stars, but with an ultra-hot plasma of particles, buzzing like a swarm of invisible bees. As the universe expanded and cooled, this chaos began to settle. Protons and electrons combined to form the first atoms, hydrogen and helium, the simplest and lightest elements in existence. This was the universe's raw material, a pristine fog of gas stretching evenly across the newborn cosmos. But even isn't quite right. Tiny fluctuations in density, smaller than ripples on a pond, were already woven into the fabric of space. These imperfections, born from quantum jitters in the universe's first moments, became the seeds of cosmic structure. Over eons, gravity amplified these faint wrinkles, pulling gas into denser patches where galaxies would eventually form. Yet not all the gas was destined to be locked away inside stars and galaxies. Some remained in the vast spaces between them, stretched into filaments by the expanding universe like taffy pulled thin. So why didn't all the gas collapse into galaxies? Picture a cosmic tug of war. Gravity works tirelessly to pull gas inward, but the universe's expansion fights back, stretching space itself and slowing gravity's grip. In denser regions, gravity won, forging galaxies. But in the voids, expansion kept gas diffuse, leaving it suspended in a delicate balance. This leftover gas, the intergalactic medium, became the universe's hidden reservoir, a slow-moving river feeding galaxies over billions of years. But there's another twist. Supernova and quasars, the universe's titanic engines, didn't just consume gas, they blew it back out. When massive stars exploded, they hurled heavy elements into the void, enriching the intergalactic medium with carbon, oxygen, and iron. Quasars, powered by ravenous black holes, shot out jets of energy that pushed gas far beyond their host galaxies. This recycling process turned intergalactic space into a cosmic junkyard and a construction site simultaneously scattered with the debris of dead stars, yet brimming with the ingredients for new ones. Today, we can still see echoes of this ancient gas in the dim glow of distant quasars. As their light passes through intergalactic space, it paints a fingerprint of absorption lines, a barcode revealing the gas's composition, temperature, and motion. These clues tell us the gas isn't just a relic, it's an active participant in cosmic evolution, cooling and flowing into galaxies even now, continuing the cycle that began at the dawn of time. If gravity is the universe's great gatherer, pulling matter into galaxies like a cosmic magnet, then why isn't all intergalactic gas sucked into these stellar cities? The answer lies in a dramatic tug of war between creation and destruction, a cycle where gas isn't just consumed, but flung back into the void with astonishing force. Picture a galaxy not as a passive trap, but as a bustling factory where stars are born, live out their lives, and then explode, sending shockwaves that blast gas right back into intergalactic space. These supernovae act like cosmic catapults, hurling material outward at speeds of thousands of kilometers per second. It's not just a one-time event. It's a relentless process, with each generation of stars contributing to the Great Escape. But supernovae aren't the only players in this high-stakes game. At the heart of many galaxies, supermassive black holes lurk, and when they feed, they don't just swallow matter, they spit it back out. These monsters generate jets of energy so powerful, they can blow gas clear out of a galaxy, creating vast bubbles in the intergalactic medium. Imagine a champagne bottle uncorked in space, with streams of gas fizzing into the cosmos. These outflows can travel millions of light years, redistributing material far beyond their home galaxies. Then there's the role of cosmic winds, rivers of charged particles streaming from star-forming regions, pushing against gravity's pull like a relentless tide. In some galaxies, these winds are so intense, they strip away gas faster than new stars can form, leaving behind a galactic ghost town. Yet this isn't just loss, it's a kind of cosmic generosity. The ejected gas, now laced with heavy elements forged in stellar furnaces, enriches the intergalactic medium, seeding future generations of stars and planets with the building blocks of life. This recycling process is why the universe isn't a static museum of old galaxies, but a dynamic, ever-changing ecosystem. Without it, galaxies would either hoard all their gas, burning through it in a few furious bursts of star formation, or starve entirely, fading into darkness. Instead, the balance between inflow and outflow keeps the cosmic cycle turning, ensuring that even the emptiest voids hold the promise of new beginnings. What's truly remarkable is how delicate this equilibrium is. Too much gas escaping and galaxies wither, too little, and they choke on their own abundance. It's a dance of forces: gravity, radiation, kinetic energy, all working in concert across billions of years. And while we're only beginning to map these flows, one thing is clear: the Great Escape isn't chaos. It's the universe's way of keeping its options open. Dark matter doesn't just exist alongside intergalactic gas, it commands it. Think of the universe as a grand theater, where dark matter is the unseen stagehand, arranging the set while gas plays its visible role under the spotlight. Without dark matter's gravitational pull, the cosmic web would unravel, its delicate filaments dispersing like smoke in the wind. This invisible substance, which outweighs ordinary matter 5 to 1, doesn't interact with light or collide with atoms, yet its presence is felt everywhere. It's the reason gas doesn't float aimlessly through space, but instead gathers into the vast, thread-like structures that connect galaxies across the void. Here's how it works. Dark matter's gravity creates wells in the fabric of spacetime, subtle dimples where gas naturally pools. Imagine rolling marbles across a table with a hidden dip. They'd slow down and cluster where the surface bends. On a cosmic scale, this is exactly what happens to intergalactic gas. It streams along the contours shaped by dark matter, condensing into the dense intersections of the cosmic web where galaxies collide and stars ignite. Without this invisible framework, gas would spread uniformly, and the universe would lack the dazzling variety of galaxies, clusters, and voids we see today. The evidence is etched into the sky. When astronomers map the distribution of galaxies, they're indirectly tracing the shadowy outline of dark matter. Galaxies don't just clump randomly, they follow the hidden architecture, clinging to the densest knots and threads of the web. Even more telling is the way gas moves. By studying the faint distortions in light from distant quasars, stretched and bent as it passes through intergalactic space, scientists can reconstruct the gravitational tug of dark matter, revealing how it shepherds gas into place. But dark matter's influence isn't just about structure, it's about timing. In the early universe, ordinary matter was too hot and energetic to collapse into galaxies on its own. Dark matter, unaffected by radiation, clumped together first, creating gravitational anchors that eventually drew in gas, cooling it enough for stars to form. This cosmic delay allowed galaxies to arise in an orderly fashion rather than in a single, chaotic burst. Without dark matter's patient guidance, the universe might have burned through its gas too quickly, leaving behind a scattered handful of stars instead of the rich tapestry we see today. Yet for all its power, dark matter doesn't act alone. The relationship between dark matter and gas is a dance, not a dictatorship. As gas gathers and ignites into stars, the energy from those stars can push back, disrupting the flow of nearby gas and even altering the distribution of dark matter itself. In some galaxies, this feedback has carved vast bubbles in the intergalactic medium, proof that ordinary matter, though outnumbered, still has a voice in shaping the cosmos. The deeper we look, the clearer it becomes. Dark matter and gas are partners in an epic billion-year collaboration. One provides the blueprint, the other supplies the raw materials. Together, they've built the universe as we know it, and they're still at work weaving new structures even now. To understand the story of cosmic evolution, we can't just study what shines. We have to listen to the whispers of the unseen. For decades, astronomers faced a cosmic accounting problem that just wouldn't add up. When they tallied all the visible matter in the universe, stars, galaxies, planets, it accounted for barely half of what theory predicted should exist. This gap became known as the missing Baryon problem, one of cosmology's most stubborn puzzles. Baryons, the particles that make up ordinary matter like protons and neutrons, seem to vanish into thin space. But the truth was even stranger. They weren't missing at all. They'd been hiding in plain sight, woven into the fabric of intergalactic space as a ghostly haze of ultra-hot gas. This gas isn't just warm, it's scorching, heated to millions of degrees by the violent energy of galaxy clusters and supermassive black holes. At these temperatures, it doesn't emit visible light. Instead, it glows faintly in X-rays, a wavelength invisible to human eyes and traditional telescopes. For years, this made it nearly undetectable, like trying to spot a candle flickering in a fog. But with the launch of advanced X-ray observatories like Chandra and XMM Newton, astronomers finally began peeling back the veil. What they found was astonishing. Vast clouds of this searing gas, stretching between galaxies like a cosmic steam, containing enough material to solve the missing Baryon problem once and for all. Here's why it's so hard to detect. The gas isn't just hot, it's incredibly diffuse, with atoms spaced so far apart that a single cupful might contain just a handful of particles. To put that in perspective, the air we breathe has about 25 quintillion molecules in the same space. Yet spread across the universe, this wispy gas adds up. It's like mist on a mountain. One droplet is trivial, but an entire valley filled with mist holds buckets of water. Similarly, these thin tendrils of intergalactic gas, when summed across billions of light years, account for nearly all the universe's missing matter. But the story doesn't end there. This gas isn't just sitting idle, it's constantly in motion, cycling through the cosmic web. When galaxies collide, shock waves ripple through the intergalactic medium, heating the gas further and pushing it deeper into the voids. Meanwhile, quieter regions slowly cool, allowing gas to trickle back into galaxies, fueling new generations of stars. It's a dynamic equilibrium, with matter flowing out as fast as it falls in, maintaining a delicate balance that keeps the universe from either running dry or flooding with stars. The discovery of these hot baryons didn't just solve a textbook mystery, it reshaped our understanding of cosmic structure. We now know the universe isn't just made of glittering islands of stars, but of an ocean of invisible matter churning between them. And with next-generation telescopes like Athena on the horizon, we're poised to map this hidden realm in unprecedented detail, revealing how it shapes everything from galaxy formation to the fate of the cosmos itself. The missing Baryons were never really lost. They were just waiting for us to see the universe in a different light. Intergalactic gas isn't just fuel for the cosmos, it's a sprawling, billion-year-old archive, preserving the universe's chemical history in ways no telescope could ever capture directly. Every atom drifting between galaxies carries a story, etched by the violent deaths of stars, the explosive births of quasars, and even the faint echoes of the first generation of stars, whose light vanished long before Earth formed. To scientists, this gas is like a cosmic parchment, its elements serving as ink, recording events so ancient they predate most of the universe's structure. Take something as simple as oxygen. In the emptiness between galaxies, it's not just a lifeless element, it's a timestamp. When massive stars explode as supernova, they forge oxygen in their cores and blast it into space. By measuring how much oxygen lingers in intergalactic gas compared to lighter elements like hydrogen, astronomers can trace how many stars lived and died in a given epoch. It's like finding layers of sediment in a canyon wall, each stratum revealing a different chapter of Earth's history, except here, the canyon spans billions of light years, and the sediment is the scattered ash of dead stars. But the real treasure lies in the rarest signatures, the fingerprints of population 3 stars. These were the universe's first stars, monstrous giants hundreds of times heavier than our sun, made purely from hydrogen and helium left over from the Big Bang. They burned fast and died young, seeding the cosmos with their unique chemical legacy. No telescope has ever seen one. They vanished long ago, but their traces linger in the intergalactic medium. By hunting for minute amounts of elements like lithium or beryllium in distant gas clouds, scientists can reconstruct how these primordial titans shaped the early universe. The gas also holds darker secrets. When galaxies collide or black holes erupt, they spew not just ordinary matter, but bizarre isotopes forged in extreme conditions. Certain ratios of carbon or nitrogen isotopes, for example, can reveal whether a gas cloud was polluted by a quiet stellar death or a cataclysmic quasar outburst billions of years ago. Even the temperature of the gas tells a story. Warmer patches might mark regions where ancient supernova heated the cosmos, while cooler strands could be pristine relics of the universe's infancy, untouched by later violence. What's astonishing is how durable this record is. Unlike galaxies which churn and recycle their gas over time, the intergalactic medium changes at a glacial pace. A wisp of gas near the edge of a void might have drifted undisturbed since the universe was a fraction of its current age, its composition frozen like a mosquito in amber. By studying these time capsules, astronomers aren't just glimpsing the past, they're piecing together a grand narrative of how the universe transformed from a featureless sea of hydrogen into the chemically rich cosmos we inhabit today. Yet decoding this archive isn't easy. The signals are faint, drowned out by the glare of nearby stars or distorted by cosmic expansion. It takes instruments like the James Webb Space Telescope, tuned to catch the faint absorption lines in quasar light, to tease out these whispers. And with every new observation, the story grows richer. We're not just mapping gas, we're reading the autobiography of the universe, written in atoms scattered across the void. Why does the vast emptiness between galaxies, seemingly the coldest place imaginable, hide gas hotter than the core of a star? The answer lies in some of the most violent events the universe can produce. Picture a quasar, the brilliant beacon of a supermassive black hole feasting on matter, firing jets of energy powerful enough to outshine entire galaxies. These cosmic blowtorches don't just light up the darkness, they superheat the surrounding gas to temperatures exceeding millions of degrees. That's like taking all the water in Earth's oceans and flash boiling it in an instant. But quasars aren't the only culprits. When galaxies collide, it's not just stars that feel the shock, it's the invisible sea of gas between them. Imagine two clouds of gas slamming together at hundreds of kilometers per second. The resulting shock waves ripple outward, turning calm intergalactic currents into a raging inferno. These collisions don't just heat the gas, they stir it like a cosmic blender, mixing heavy elements forged in stellar furnaces with pristine hydrogen from the early universe. Here's where things get fascinating. This heat isn't just a side effect, it's a critical regulator, a thermostat for the cosmos. If intergalactic gas cooled too quickly, gravity would pull it wholesale into galaxies, sparking runaway star formation that would burn through fuel in a cosmic blink. Entire galaxies would flare up and die young, leaving the universe dark and lifeless. Instead, the heat acts as a brake, keeping much of the gas suspended in a diffuse, fiery haze, too energetic to collapse into stars, but not so hot it escapes the cosmic web entirely. Active galactic nuclei add another twist. When their black holes feast, they don't just radiate energy, they launch winds of charged particles at nearly light speed, scouring gas from their host galaxies and dumping it into intergalactic space. These outflows are like cosmic pressure valves, ensuring no galaxy hoards too much star-making material. The gas they expel doesn't just vanish, it lingers in the web, glowing faintly in X-rays, waiting for gravity to eventually pull it back into the cycle. The balance between heating and cooling is so precise, it's almost poetic. Too much cooling and galaxies drown in their own star-forming frenzy. Too much heating and they starve, their gas blown too far away to ever return. This equilibrium explains why some galaxies, like our Milky Way, form stars at a steady trickle, while others, caught in the crossfire of cosmic violence, become barren wastelands. What's truly remarkable is how long this dance has been going on. The same processes that heated gas near the dawn of time are still at work today, meaning the emptiness between galaxies isn't empty at all, it's a simmering ocean of energy, quietly shaping the destiny of everything it touches. And with next-generation telescopes, we're finally learning to read the ripples in this cosmic steam, uncovering how the universe tunes its own temperature to build galaxies that last. Galactic winds are the universe's great equalizers, violent storms of energy that rage through galaxies, hurling gas into the void with enough force to reshape entire cosmic landscapes. Picture a hurricane, but one that spans tens of thousands of light years, fueled not by air and water, but by exploding stars and the gravitational fury of black holes. These winds don't just blow, they sculpt. When a supernova detonates, it doesn't just light up the sky, it sends shockwaves tearing through its host galaxy, pushing surrounding gas outward like a cosmic plow. And when a supermassive black hole feasts on matter, it doesn't just swallow, it spits. Jets of charged particles erupt from its poles, accelerating gas to nearly the speed of light and launching it far beyond the galaxy's grasp. This isn't destruction, it's redistribution. Without these winds, galaxies would burn through their gas reserves in a few furious bursts of star formation, collapsing into stagnant graveyards of dead stars. Instead, the ejected gas becomes part of a vast recycling program. Some of it falls back into the galaxy later, cooled and enriched with heavy elements, ready to fuel new generations of stars. The rest mingles with the intergalactic medium, seeding future galaxies with the raw materials for planets, and perhaps even life. The scale of these outflows is staggering. In galaxies like Messier 82, winds have been observed carrying gas at speeds of over 2 million kilometers per hour, enough to empty the galaxy of its star-forming fuel within a few 100 million years. Yet, paradoxically, these winds also sustain galaxies in the long run. By preventing all the gas from collapsing into stars at once, they stretch out a galaxy's lifespan, allowing it to evolve gradually rather than flame out in a single, brilliant burst. What's truly fascinating is how these winds leave their mark on the cosmos. As they travel, they drag heavy elements like oxygen, carbon, and iron forged in the hearts of stars into intergalactic space. This pollution might sound like a bad thing, but it's essential. Before these winds, the voids between galaxies were pristine, filled only with the hydrogen and helium left over from the Big Bang. Now they're laced with the building blocks of rocky planets and organic molecules, scattered by the very forces that once threatened to starve galaxies of their fuel. Studying these winds is like reading the diary of a galaxy's life. By measuring their speed, composition, and temperature, astronomers can reconstruct a galaxy's history of star formation and black hole activity. Some winds are gentle breezes carrying traces of quiet stellar deaths. Others are gales, bearing the signature of catastrophic collisions or quasar eruptions. Together, they reveal how galaxies don't exist in isolation. They're constantly in conversation with the cosmos, exchanging matter and energy with the vast networks around them. And the story isn't over. Even now, winds from distant galaxies are shaping the universe's future, ensuring that the next generation of stars will have the resources they need to shine. Far from being agents of chaos, these winds are the unseen architects of cosmic balance, threading the needle between too much and too little, between creation and dispersal. Without them, the night sky would be a very different place, and so would we. In the searing ocean of intergalactic gas, where temperatures soar to millions of degrees, there are islands of cold, strange, dense pockets of gas chilling at just a few degrees above absolute zero. These cosmic anomalies shouldn't exist. Like ice cubes floating in boiling water, they defy logic, surviving in an environment that should vaporize them instantly. Yet here they are, scattered across the cosmic web, some so dense they cast shadows on the light of distant quasars. What's keeping these frozen relics intact in a universe that's overwhelmingly hot? One clue lies in their birthplaces. Many of these cold clumps are found near the fringes of galaxy clusters, where the turbulent winds of star formation and black hole activity have died down. Picture a bustling city center versus a quiet suburb. The outskirts are calmer, shielded from the chaos. In these quieter regions, gas can slowly radiate away its heat, cooling over millions of years until it condenses into these mysterious, frosty knots. But that's not the only way they form. Some might be the shattered remains of ancient gas clouds, torn apart by gravitational tides, yet stubbornly refusing to dissipate, like fragments of a shipwreck drifting in a hostile sea. Even more intriguing is what these clumps could become. Under the right conditions, their extreme density makes them perfect nurseries for future galaxies. Gravity works faster on cold, compact gas, pulling it together before heat can blow it apart. In the early universe, similar clumps may have been the seeds of the first galaxies, collapsing under their own weight while the surrounding gas was still too hot to coalesce. Today's cold pockets could be doing the same, quietly gathering mass, waiting for the moment they ignite into new stellar metropolises, but their survival is a puzzle. How do they avoid being reheated by nearby supernova or the blistering radiation from quasars? The answer might lie in magnetic fields. Like an invisible shield, these fields could wrap around the clumps, insulating them from the surrounding inferno. Alternatively, the gas might be laced with trace amounts of molecules like hydrogen or carbon monoxide, which act like cosmic refrigerants, helping it shed heat faster than the environment can replenish it. What's certain is that these cold clumps are more than cosmic oddities. They're laboratories for testing our understanding of gas dynamics. If our models can't explain how they persist, we might be missing a fundamental piece of how structure forms in the universe. Every new observation peels back another layer of the mystery, revealing a cosmos far more nuanced than we ever imagined. The hot and the cold, the diffuse and the dense, they're all part of the same grand tapestry, woven together by forces we're only beginning to comprehend. Magnetic fields might be invisible, but their fingerprints are all over the cosmos, etched into the swirling currents of intergalactic gas like cosmic handwriting. Though these fields are faint, often millions of times weaker than a common refrigerator magnet, they wield surprising influence over the universe's largest structures. Picture a river guided by an unseen hand. Magnetic fields don't just nudge gas flows, they sculpt them, twisting streams into spirals, amplifying turbulence, and even shielding fragile gas clouds from the destructive forces of superheated plasma. Without these subtle forces, galaxies might never have formed the way we see them today. Take the vast filaments of the cosmic web. Gas flowing along these threads doesn't move randomly. It's channeled by magnetic fields, like water funneled through an invisible pipe. These fields act as cosmic traffic directors, ensuring gas doesn't spill chaotically into the voids, but instead streams efficiently toward galaxy clusters, where it can fuel star formation. In some cases, they even create magnetic highways, accelerating particles to near light speeds and producing faint radio emissions detectable across billions of light years. But their most dramatic role might be as protectors. When a gas cloud drifts too close to a galaxy's supermassive black hole or the blistering jets of a quasar, it should be ripped apart by intense radiation and shock waves. Yet some clouds survive thanks to magnetic fields wrapping around them like a shield. These fields deflect charged particles and stabilize the gas, preventing it from dispersing into the surrounding inferno. It's like a delicate soap bubble holding its shape in a hurricane, defying the chaos around it. The origins of these fields are just as fascinating. Some were born in the early universe, stretched and amplified by the expansion of space itself. Others were forged later, woven into existence by the motion of ionized gas in galaxies, then blown into intergalactic space by supernova explosions or quasar winds. Once out there, they self-perpetuate, growing stronger as turbulent gas motions twist and fold them, much like kneading dough strengthens gluten strands. Yet for all their importance, mapping these fields remains a monumental challenge. They don't emit light, and their effects are often subtle, visible only in the way they polarize distant starlight or influence the paths of cosmic rays. New techniques like studying the alignment of dust grains or the faint glow of synchrotron radiation are finally pulling back the curtain on this hidden force. What we're learning reshapes our understanding of cosmic evolution. Magnetism isn't just a footnote, it's a co-author of the universe's grand story. The implications ripple across astrophysics. Simulations that ignore magnetic fields often produce galaxies that are too smooth, too orderly, failing to match the tangled beauty we observe. Add magnetism back in, and suddenly gas behaves more realistically, clumping into denser knots and forming the intricate spiral arms we see in galaxies like our Milky Way. It's a reminder that the universe doesn't rely solely on gravity to build its structures. Sometimes, the quietest forces leave the boldest marks. The universe is the ultimate alchemist, tirelessly transmuting the simplest elements into the building blocks of life, and intergalactic gas is its delivery system. While hydrogen and helium dominate this cosmic reservoir, trace amounts of heavier elements like oxygen, carbon, and iron drift between galaxies like dust motes in a sunbeam. These aren't just impurities, they're the ashes of dead stars scattered across the cosmos by supernova explosions and galactic winds. Every atom of gold in a wedding ring, every speck of calcium in your bones, began its journey in the heart of a dying star before hitchhiking through intergalactic space to reach Earth. This chemical enrichment didn't happen all at once. In the early universe, intergalactic gas was pristine, pure hydrogen and helium left over from the Big Bang. The first generation of stars, massive and short-lived, changed everything. When these titans exploded, they fused lighter elements into heavier ones, ejecting them into the void in fiery bursts. Over billions of years, successive generations of stars repeated this process, each contributing new elements to the cosmic mix. Today, even the most remote gas clouds bear the chemical fingerprints of countless stellar deaths, a testament to the universe's relentless recycling program. The distribution of these elements tells a story of cosmic pollution on the grandest scale. Near galaxies, gas is rich in heavy elements, like smoke lingering near a factory. Farther out, the concentrations drop, but they never disappear entirely. Quasars act as cosmic flashlights, their light absorbed by these metal-rich gas clouds, revealing telltale spectral lines. By mapping these absorption features, astronomers have uncovered vast regions where gas is laced with iron from supernova or oxygen from red giants, elements carried far beyond their birthplaces by galactic winds. What's astonishing is how efficiently this material travels. Some gas clouds contain elements forged in galaxies millions of light-years away, proof that the cosmos is interconnected on scales we're only beginning to grasp. When two galaxies collide, their intergalactic gas mingles, blending elements from both in a celestial cocktail. Over time, this mixed gas can cool and fall back into galaxies, seeding new stars and planets with a richer variety of materials. Without this process, rocky planets like Earth might never have formed, and life as we know it would lack the chemical complexity to arise. But the story isn't just about abundance, it's about balance. Too many heavy elements and gas cools too quickly, collapsing into stars before galaxies can grow to their full size. Too few, and planets remain barren, devoid of the minerals needed to sustain life. The universe walks a tightrope, with supernova and galactic winds fine-tuning the chemical mix over eons. Now, telescopes like the James Webb Space Telescope are peering even deeper into this narrative, spotting gas clouds enriched by the very first stars. These ancient pockets are time capsules, preserving the universe's earliest attempts at chemistry. By comparing them to younger gas clouds, we're unraveling how the cosmos transformed from a sterile expanse into a fertile ground for planets, and perhaps life beyond Earth. The next time you take a breath, remember, the oxygen filling your lungs once sailed through the voids between galaxies, a stowaway on the greatest recycling journey of all time. The universe we see today, brimming with galaxies, stars, and light, is a fleeting spectacle in cosmic terms. Right now, intergalactic gas acts as the lifeblood of creation, funneling into galaxies and igniting new stars. But this era of abundance won't last forever. As the cosmos expands, the vast reservoirs of gas between galaxies will stretch thinner and thinner, like ink diluted in an ever-growing ocean. Over time, this dilution will starve galaxies of their fuel, slowing star formation to a trickle until eventually the lights go out. The universe isn't just aging, it's running out of raw materials. Consider the fate of a single hydrogen atom drifting in intergalactic space today. Billions of years from now, as the universe continues expanding, that atom will find itself increasingly isolated, separated from others by distances so vast that gravity can no longer pull them together. Galaxies, too, will grow more distant, their gravitational pull weakening as the space between them stretches. Without fresh infalls of gas, star formation will sputter out, leaving galaxies to fade into darkness as their existing stars burn out one by one. The last stars to ignite small, dim red dwarfs may shine for trillions of years, but even they will eventually flicker away, leaving behind a cosmos of black holes and cooling stellar remnants. This bleak future, known as the heat-death scenario, isn't just theoretical. We're already seeing hints of it today. Observations show that star formation rates peaked around 10 billion years ago and have been declining ever since. The universe's golden age of galaxy building is behind us, and the decline will only accelerate as gas grows scarcer. Yet this grim trajectory makes our current era all the more precious. Right now, we live in a sweet spot, late enough to witness a universe rich with structure, but early enough to catch intergalactic gas in action, still shaping galaxies and birthing stars. Studying this gas today is like reading a dying language before it vanishes. Each observation captures a snapshot of processes that will one day cease, helping us piece together how the universe builds and loses its grand structures. Missions like the upcoming European Space Agency's Athena X-ray Observatory aim to map the faint glow of intergalactic gas in unprecedented detail, tracing how it flows, heats, and cools. These observations won't just illuminate the present, they'll help us predict the universe's ultimate fate. But there's a twist. While the big picture looks bleak on cosmic timescales, local pockets of activity might persist far longer. In galaxy clusters where gas is densely concentrated, star formation could continue long after the rest of the universe goes dark. And some theorists speculate that advanced civilizations, if they exist, might find ways to harvest the last wisps of intergalactic gas, stretching out the era of starlight a little further. The lesson here isn't just about cosmic doom, it's about urgency. The window for understanding intergalactic gas won't stay open forever. By studying it now, we're not just solving today's mysteries, we're preserving knowledge for a far future when the universe itself will have forgotten how galaxies were born. Every observation is a time capsule, a message to the future about how a vibrant cosmos once worked. And that makes our current era, fleeting as it is, one of the most important chapters in the universe's story. Galaxy clusters are the titans of the cosmos, colossal cities of thousands of galaxies bound together by gravity, each one pulsing with energy. But the real powerhouses of these clusters aren't the glittering galaxies we see. They're the vast oceans of superheated gas that fill the spaces between them. This gas isn't just lingering debris. It's a seething, X-ray glowing plasma, hotter than the core of a star, stretching across millions of light years. And it holds secrets that rewrite our understanding of gravity, dark matter, and the very structure of the universe. When astronomers first pointed X-ray telescopes at galaxy clusters, they expected to see faint whispers of radiation. Instead, they found a roaring blaze. The gas in these clusters is so hot, it emits X-rays with such intensity that they outshine all the stars in the cluster combined. This isn't just a cosmic curiosity, it's a goldmine of information. By analyzing the X-rays, scientists can map the gas's temperature, density, and even its motion, revealing how these clusters grow and evolve over billions of years. One of the most astonishing discoveries is how this gas acts as a cosmic scale. Galaxy clusters are so massive, they warp spacetime itself, bending the light of distant objects behind them in a phenomenon called gravitational lensing. But when astronomers compared the lensing measurements with the mass of the visible galaxies, the numbers didn't add up until they accounted for the intergalactic gas. This invisible plasma accounts for far more mass than all the stars in the cluster combined, acting as a hidden counterweight that helps calibrate the universe's largest structures. The gas also serves as a tracer for something even more elusive, dark matter. Since dark matter doesn't interact with light, it's impossible to observe directly. But its gravitational pull shapes the distribution of hot gas, sculpting it into telltale patterns. By studying these distortions, astronomers can reconstruct the invisible skeleton of dark matter that holds the entire cluster together. It's like watching wind ripple the surface of a pond to deduce the shape of the submerged rocks below. Perhaps the most revolutionary use of this gas is testing the laws of gravity themselves. Einstein's theory of general relativity has passed every test on Earth and in the solar system, but does it hold up in the extreme environments of galaxy clusters? The hot gas, subjected to titanic gravitational forces, behaves like a cosmic laboratory. Tiny deviations in its movement could hint at new physics, suggesting that gravity operates differently on the largest scales. Some researchers even speculate that these anomalies might point to alternatives to dark matter, a cosmic paradigm shift waiting in the data. Yet the gas isn't just a passive tool, it's a dynamic player in the cluster's life cycle. When galaxies within the cluster move, they stir the gas like spoons in a boiling pot, creating shock waves and turbulence. Some galaxies, plunging through the cluster's center, have their own gas stripped away by the sheer pressure, leaving them barren and starved. Others, drifting in quieter regions, slowly accrete gas from their surroundings, fueling new generations of stars. This interplay between galaxies and their gaseous environment shapes the destiny of the entire cluster, determining which galaxies thrive and which fade into darkness. What's truly remarkable is how long this gas persists. Unlike stars which burn out or galaxies which merge and change, the hot gas in clusters remains a near-permanent fixture, slowly cooling over billions of years but never disappearing entirely. It's a fossil record of the cluster's history, preserving the echoes of ancient collisions, explosions, and inflows. By reading its faint X-ray signature, we're not just observing the present, we're decoding the autobiography of the universe's most massive structures. And the story isn't over. With next-generation X-ray telescopes like Lynx and Athena on the horizon, we're poised to peer even deeper into these glowing seas of gas, uncovering secrets about dark energy, cosmic expansion, and the ultimate fate of the universe itself. The hot gas in galaxy clusters isn't just a backdrop. It's the key to understanding everything from the tiniest particles to the grandest scales of existence. Simulating the universe isn't just about crunching numbers, it's about rewinding time. Inside the world's most powerful supercomputers, trillions of particles of virtual gas dance to the laws of physics, recreating cosmic history from the Big Bang to the present day. These aren't simple animations, they're precision-engineered universes where every gravitational tug, every collision, and every burst of stellar radiation is calculated down to the smallest detail. The goal: to decode the invisible forces that have shaped our cosmos, forces we can't replicate in any lab on Earth. Take the Illustris TNG project, one of the most ambitious simulations ever attempted. It doesn't just model gas as a homogeneous cloud, it treats it as a dynamic fluid, complete with turbulence, magnetic fields, and even the chemical enrichment from exploding stars. When researchers hit start, they watch virtual galaxies form in fast-forward, their gas swirling into spiral arms or funneling into black holes with eerie accuracy. The simulations match real telescope observations so closely, they've become a Rosetta Stone for interpreting the messy, chaotic processes we see in the actual universe. But why rely on simulations when we have telescopes? Because some cosmic processes unfold over billions of years, far too slowly for humans to witness directly. Imagine trying to understand the life cycle of a forest by only ever seeing a single snapshot. You'd miss the growth of the trees, the fall of the leaves, the regeneration after a fire. Simulations let us compress cosmic timescales into days or weeks, revealing patterns that would otherwise take millennia to emerge. They've uncovered hidden phenomena, like how galactic winds can strip gas from smaller galaxies, leaving them starved and dim, or how black holes regulate star formation by heating intergalactic gas like cosmic thermostats. The secret sauce lies in the feedback loops. In the real universe, when stars explode or black holes erupt, they don't just vanish. They send shockwaves through their surroundings, altering the very gas that might form the next generation of stars. Simulations capture this self-regulating dance, showing how galaxies avoid either burning through their gas too quickly or hoarding it uselessly. Without these virtual experiments, we might never have realized how delicately balanced these systems are, how a slight change in supernova energy or black hole activity could leave a galaxy barren or overflowing with stars. Yet even the most advanced simulations have limits. Modeling every atom in a galaxy is impossible. Instead, scientists use clever shortcuts, treating gas as clumps or particles that represent vast clouds. It's like painting a landscape with broad brushstrokes. The overall picture looks right, but zoom in, and the details blur. That's why simulations constantly evolve, borrowing techniques from weather forecasting and fluid dynamics to refine their accuracy. Each breakthrough, like adding quantum mechanics or dark matter interactions, brings the virtual cosmos closer to reality. What's truly groundbreaking is how these simulations predict discoveries. Before telescopes spotted the first dark galaxies, starless clumps of gas lurking in the void, simulations had already hinted they might exist. When astronomers found evidence of gas filaments connecting galaxy clusters, simulations had mapped similar structures years earlier. It's a virtuous cycle. Observations test the simulations, and the simulations guide new observations. Together, they're rewriting the story of cosmic evolution, revealing a universe far more dynamic and interconnected than we ever imagined. So the next time you see a breathtaking galaxy in a telescope image, remember, it's not just a static snapshot. Behind the scenes, supercomputers are unraveling its history, tracing the invisible rivers of gas that brought it to life. They're the time machines of modern astrophysics, letting us journey not just across space but through the eons. The first stars didn't just light up the universe, they rewrote it. Born from clouds of pure hydrogen and helium, these primordial giants, known as Population 3 stars, were unlike anything we see today. Imagine a star 100 times more massive than our Sun, burning at temperatures so extreme it lived fast and died young, collapsing in a cataclysm that seeded the cosmos with the first heavy elements. Their light has long since faded. Their bodies vanished into black holes or scattered as supernova debris. Yet their legacy lingers, etched into the very fabric of intergalactic gas like whispers from the dawn of time. What makes these stars so special isn't just their size, it's their purity. They formed from gas untouched by previous generations, free of the carbon, oxygen, and iron that fill modern stellar nurseries. This pristine environment meant they burned hotter, brighter, and more violently than any star since. When they exploded, they didn't just die, they transformed the universe, flooding space with the first traces of elements beyond hydrogen and helium. These elements became the building blocks for everything that followed: the next generation of stars, the first rocky planets, and eventually the chemistry of life itself. But how do we study something that vanished over 13 billion years ago? The answer lies in the shadows they cast. As the light of the first stars illuminated the surrounding gas, it altered the gas's properties in subtle ways. Specifically, their ultraviolet radiation ionized neutral hydrogen, stripping electrons from atoms and leaving behind a faint fingerprint in the way gas absorbs light from even more distant objects like quasars. By scouring quasar spectra for these absorption features, astronomers can hunt for the ghostly echoes of population 3 stars, like detectives analyzing faint stains on an ancient relic. The challenge is separating these whispers from the cosmic noise. Intergalactic gas has been stirred, heated, and polluted by eons of supernova and galaxy collisions, obscuring the primordial signal. But there are clues. Certain regions of the gas, particularly in the emptiest voids, may have remained undisturbed, preserving traces of that first stellar light. Others might show unusual ratios of elements like an overabundance of lithium or beryllium that could only have been produced in the cores of those early behemoths. The hunt isn't just academic. Understanding population 3 stars means understanding how the universe transitioned from simplicity to complexity. They were the bridge between the smooth, featureless cosmos of the Big Bang and the structured, galaxy-filled universe we see today. Their explosions created the first shock waves, compressing nearby gas and triggering the formation of the second generation of stars smaller, longer-lived, and more stable. Without them, galaxies as we know them might never have formed. New telescopes like the James Webb Space Telescope are finally bringing these elusive stars within reach. By peering back to the universe's infancy, they could catch the telltale glow of population 3 stars in their final moments, or the chemical signatures they left behind in ancient gas clouds. Each observation is a step closer to solving one of cosmology's greatest mysteries: how darkness gave way to light, and how the first sparks of star life set the stage for everything that followed. Yet, even if we never spot one directly, their influence is undeniable. Every atom of oxygen in your lungs, every speck of iron in your blood, traces back to stars that lived and died long before our sun was born. And among those early pioneers, the first stars hold a singular place: the architects of cosmic chemistry, the alchemists that turned simplicity into diversity. Their story isn't just about the past, it's about the origins of everything we are. Could the seeds of life be drifting between galaxies, hidden in the vast clouds of intergalactic gas? It's a radical idea, one that challenges our planet-centric view of biology, but recent discoveries suggest the building blocks of life might be more widespread than we ever imagined. Take the discovery of complex organic molecules like methanol and formaldehyde in distant gas clouds. These aren't just simple chemicals, they're the precursors to amino acids, the very foundation of proteins. If these molecules can form in the emptiness between galaxies, what else might be lurking there? The concept of life in intergalactic space sounds like science fiction, but the physics isn't as far-fetched as it seems. In the dense cores of some gas clouds, temperatures plummet close to absolute zero, creating environments where molecules can clump together without being torn apart by heat or radiation. Some theories even suggest that microbial life, if it existed, could hitch a ride on dust grains, shielded by layers of ice, a kind of cosmic stowaway drifting between star systems. It's a long shot, but not impossible. After all, we've already found extremophiles on Earth thriving in places once thought uninhabitable, from volcanic vents to the vacuum of space. What's truly fascinating is the role intergalactic gas might play in spreading life across the cosmos. Imagine a galaxy teeming with life, its planets rich with microbes. When a supernova explodes or a black hole erupts, the resulting shockwaves could blast fragments of rock and any hitchhiking organisms into intergalactic space. These fragments, encased in protective shells of ice, might drift for millions of years before being captured by another galaxy's gravity. It's a slow process, but on cosmic timescales, it could be enough to seed life far beyond its origin point. Of course, the biggest hurdle is energy. Life as we know it needs a source of sustenance, and the sparse gas between galaxies offers little in the way of food. But what if life there doesn't operate like Earth's? Some researchers speculate that exotic forms of biology could evolve to harness energy from cosmic rays or even the faint glow of starlight. Others suggest that life might enter a dormant state, waking only when it stumbles into a more hospitable environment, like a planet or a star-forming nebula. The search for such life would require entirely new tools. Traditional methods like scanning for radio signals or analyzing planetary atmospheres won't work in the diffuse reaches of intergalactic space. Instead, astronomers might look for unusual chemical signatures, clusters of complex molecules, or unexpected imbalances in gas composition that hint at biological activity. Future telescopes with sensitivity to detect faint molecular traces across vast distances could turn this speculative idea into a testable hypothesis. Even if life isn't out there, the mere possibility reshapes how we think about our place in the universe. If life can arise not just on planets, but in the void itself, then the cosmos might be far more alive than we ever dared imagine. The next great discovery in astrobiology might not come from a distant exoplanet, but from the silent, invisible rivers of gas flowing between the stars. Some of the universe's most puzzling objects aren't dazzling spirals or radiant clusters, they're ghostly silhouettes, galaxies so faint they barely register against the blackness of space. Yet hidden within these cosmic phantoms lies a shocking secret. Reservoirs of gas so vast they could birth thousands of stars. These are dark galaxies, the universe's greatest underachievers, flouting every rule we thought we knew about how galaxies shine. What makes them so strange? Picture a galaxy-sized cloud of hydrogen gas, hundreds of millions of times the mass of our Sun, drifting undisturbed for billions of years. Under normal circumstances, gravity would compress this gas into dense knots, igniting stars and lighting up the darkness. But in dark galaxies, something stalls this process. Maybe the gas is too spread out, like flour dusted too thinly to ever form dough. Or perhaps magnetic fields crisscrossing the gas act like cosmic scaffolding, preventing collapse. Some theories even suggest these galaxies are trapped in cosmic voids, isolated from the collisions and interactions that typically trigger star formation elsewhere. The discovery of these shadowy systems came from an ingenious workaround. Since they emit almost no visible light, astronomers hunt for them by observing how they distort the radio waves from background objects. One of the most famous, a galaxy dubbed Dragonfly 44, contains enough dark matter to rival the Milky Way, but produces just 1% of its starlight. Others, like the ultra-diffuse galaxies in the Coma cluster, stretch as wide as our galaxy while hosting only a flicker of stars. Their gas reservoirs glow faintly in radio telescopes, revealing the raw materials for stellar birth that somehow never ignite. These failures might actually hold the key to understanding galactic success. Dark galaxies could represent a frozen early stage of development, snapshots of what all galaxies looked like before star formation began. If true, studying them is like finding a cosmic fossil, a pristine relic from an era when the universe hadn't yet learned to shine. Alternatively, they might be galactic burnouts, systems that exhausted their star, making potential too quickly and faded into obscurity. Their gas could have been heated by ancient supernova or black holes, leaving it too agitated to coalesce into new stars, the most tantalizing possibility. Dark galaxies might be absorbing intergalactic gas even now, quietly amassing fuel for a future explosion of stellar birth. Some simulations suggest these systems could be galaxies in waiting, biding their time until a collision or density wave triggers their transformation. If so, we might be witnessing the cosmic equivalent of a seed lying dormant, waiting for rain. Whatever their story, dark galaxies force us to rethink what makes a galaxy alive. Is it the brilliance of its stars or the potential humming in its unseen gas? As telescopes like the Square Kilometre Array come online, capable of mapping hydrogen gas with unprecedented precision, we may finally solve the riddle of these cosmic ghosts and, in doing so, rewrite the book on how all galaxies are born. Quasars don't just light up the cosmos, they rewrite its very chemistry. These titanic beacons, blazing from the hearts of distant galaxies, are more than just cosmic oddities. They're the universe's ultimate alchemists, wielding radiation so intense it can strip electrons from atoms across millions of light years. This process, called ionization, doesn't just tweak the properties of intergalactic gas, it reshapes the fabric of the cosmos itself, turning what was once a fog of neutral hydrogen into a transparent sea of charged particles. And the echoes of this transformation, which began over 13 billion years ago, are still visible today in the faint glow of gas clouds illuminated by quasars' long-dead light. The story starts in the universe's murky adolescence, a period known as the Dark Ages. Back then, space was filled with a thick haze of neutral hydrogen gas, absorbing starlight like a cosmic fog bank. But as the first quasars flickered to life, their ultraviolet radiation began punching holes in this fog, ionizing the gas and rendering it transparent. Think of it like a frost-covered window gradually clearing as sunlight warms the glass, except here, the window is the entire observable universe, and the sunlight is the combined fury of countless quasars. This epoch, called reionization, marked one of the most profound transitions in cosmic history, lifting the veil that had shrouded the early cosmos and allowing light to travel freely for the first time. What's astonishing is how far-reaching a single quasar's influence can be. The brightest quasars emit more energy in a second than our Sun will in its entire lifetime, and their radiation cones carve out vast bubbles of ionized gas in the intergalactic medium. These bubbles aren't static, they expand over time, merging with others like soap suds in a sink, until eventually the entire universe is ionized. Telescopes have spotted quasars whose ionization fronts stretch tens of millions of light years, their radiation fingerprint detectable in the absorption lines of gas clouds billions of years later. It's like finding the scorch marks of a wildfire that burned when Earth was still molten. But quasars don't just ionize gas, they fingerprint it. As their light passes through intergalactic clouds, specific wavelengths get absorbed, creating a barcode-like pattern in the quasar's spectrum. Each line in this barcode corresponds to an element or ionization state, revealing the gas's temperature, density, and even its motion. By studying these absorption lines, astronomers can reconstruct how the universe evolved from a neutral soup to the ionized expanse we see today. Some quasars even show proximity zones, regions near the quasar where the gas is so thoroughly ionized, it's nearly empty, a cosmic clearing carved by relentless radiation. The timing of reionization is a critical clue to the universe's history. Observations suggest the process began around 400 million years after the Big Bang and took another 500 million years to complete. But here's the puzzle. There don't seem to be enough quasars in the early universe to explain the speed of reionization. This has led scientists to suspect that other actors, perhaps the first generation of stars or even exotic particles, lent a hand. Quasars might have been the flashiest players, but they likely didn't work alone. Today, the legacy of quasars is written in the sky. The cosmic microwave background, the afterglow of the Big Bang, bears subtle imprints of reionization like waves frozen in time. Meanwhile, telescopes like the James Webb Space Telescope are peering back to the era when the first quasars ignited, watching in real time as they punch through the cosmic fog. Each discovery tightens the timeline, helping us understand not just how the universe became transparent, but how it grew into the structured, galaxy-filled place we call home. And the story isn't over. Even now, quasars continue to ionize gas, their influence echoing across the eons. They're not just relics of the past, they're reminders of how the most violent forces in the cosmos can also be the ones that illuminate our understanding. Hidden in the blackness between galaxies, vast clouds of hydrogen gas glow with an eerie, uniform light not from stars or quasars, but from some unseen cosmic engine. These are Lyman-alpha blobs, some of the largest and most mysterious structures in the universe, stretching wider than entire galaxy clusters and shining with the faint signature of ionized hydrogen. Named for the specific wavelength of ultraviolet light they emit, these blobs defy easy explanation. They shouldn't be visible at all. Their gas is too diffuse, too cold, yet there they are, luminous ghosts floating in the void. What could possibly power such enormous, isolated beacons? One leading theory points to newborn galaxies buried deep within the blobs. As these galaxies churn out massive stars, their intense ultraviolet radiation excites the surrounding hydrogen, causing it to fluoresce like a neon sign in the cosmic dark. Another possibility involves supermassive black holes at the blob's cores, their voracious feeding launching shockwaves that heat the gas and make it glow. But the most tantalizing idea is that these blobs are cosmic wombs, regions where gravity is slowly gathering gas into the next generation of supergalaxies, structures so vast they'll one day dominate their corners of the universe. The scale of these blobs is almost incomprehensible. The largest, like the one nicknamed Lab 1, span nearly 300,000 light-years, 3 times the width of our Milky Way. Yet despite their size, they're incredibly faint, visible only through the most sensitive telescopes tuned to the Lyman-alpha wavelength. It's like trying to spot a dimly lit cloud floating in the depths of the ocean, illuminated only by the occasional flicker of bioluminescence. What makes them even stranger is their structure. Unlike the chaotic swirls of star-forming nebulae, Lyman-alpha blobs often appear smooth and symmetrical, their light evenly distributed as if painted onto the cosmos. This suggests the gas within them is being energized by something pervasive, perhaps a uniform bath of radiation from an unseen source, or the slow, steady infall of material onto a growing galactic core. Some blobs even show intricate filaments, like veins in a leaf, hinting at hidden currents of gas flowing along magnetic field lines. The discovery of these blobs has forced astronomers to rethink how galaxies form. Conventional wisdom says galaxies grow by pulling in gas from their surroundings, but Lyman-alpha blobs suggest the process might be more collaborative, like rain condensing around dust particles. Galaxies may form within these glowing gas reservoirs, drawing material from the surrounding fog. If true, it would mean the blobs aren't just bystanders, they're active participants in galactic evolution, shaping the destiny of the stars and planets that will one day form inside them. Yet for all their importance, Lyman-alpha blobs remain shrouded in mystery. Why do some glow brighter than others? Why are they so rare, scattered across the universe like distant lighthouses? And what determines their bizarre shapes, some round, others elongated, as if stretched by invisible hands? Each new observation peels back another layer, revealing a universe far more complex and interconnected than we ever imagined. One thing is certain, these glowing enigmas are more than just cosmic curiosities. They're windows into the forces that built the universe, the quiet, invisible processes that turn emptiness into structure, darkness into light. And as telescopes grow more powerful, we may soon uncover their secrets, learning not just how galaxies are born, but how the cosmos itself learned to shine. What if the rivers of gas flowing between galaxies aren't just cosmic leftovers but echoes of other universes? It sounds like science fiction, but some physicists are seriously considering whether the patterns in intergalactic gas could be scars from collisions with parallel realities. This isn't just wild speculation, it's a frontier of cosmology, where the faintest wrinkles in the cosmic web might rewrite our understanding of existence itself. The idea hinges on multiverse theory, which suggests our universe is one bubble in an infinite froth of others, each with its own laws of physics. If these bubbles occasionally brush against one another, the impact could send shockwaves through space, subtly warping the distribution of gas in ways that linger for billions of years. Think of it like finding a fingerprint on a window pane, except the window is the observable universe, and the fingerprint belongs to a reality we can't otherwise see. Signatures of these collisions might hide in the cosmic microwave background, the afterglow of the Big Bang, where unexplained anomalies like the cold spot could be bruises from a long-ago encounter. But intergalactic gas adds another layer. Unlike the smooth microwave background, gas filaments are clumpy and irregular, offering more places for oddities to hide. Simulations show that a universe collision could stretch gas into unusual alignments or create voids where logic says there shouldn't be any. The challenge: distinguishing these anomalies from ordinary cosmic turbulence. Skeptics argue it's a needle in a haystack problem. With so many natural processes shaping gas, why invoke other universes? Yet proponents counter that some patterns defy conventional explanations. Take the axis of evil, a mysterious alignment of galaxy clusters that seems to point in a preferred direction, as if something beyond our universe tugged them into place. Could it be gravity leaking through from a neighboring cosmos? Or is it just a statistical fluke? The debate rages, but the mere possibility has spurred new ways to map gas with next-gen telescopes, hunting for irregularities no standard model can explain. Even if the evidence remains elusive, the theory reshapes how we see intergalactic gas. No longer just fuel for stars, it becomes a cosmic message board, where universes might scroll notes to one another across the void. And if we ever decode those messages, the answer wouldn't just solve a mystery, it would prove we're not alone in the grandest sense imaginable. The gas between galaxies, it turns out, might be the thinnest of veils, hiding realities beyond our wildest dreams. Exploring the cosmos isn't just a scientific endeavor, it's an ethical frontier. As we train our telescopes on the delicate filaments of intergalactic gas, mapping their flows and decoding their chemistry, we're forced to confront an uncomfortable question: do we have the right to interfere? Consider the cosmic web, a structure so fragile that the gravitational tug of a passing galaxy can alter its course over millennia. Now imagine our own interventions, future technologies that might siphon gas for fuel or manipulate its distribution to engineer star formation. What unintended consequences could ripple across billions of years? The very act of observation changes what we study. The light we use to probe these distant clouds carries energy that subtly alters their properties, like a doctor's touch warming a thermometer. This dilemma mirrors humanity's historical struggles with unexplored frontiers. When European explorers first charted the oceans, they couldn't foresee how their maps would enable overfishing or pollution. Similarly, our cosmic surveys might one day enable resource extraction on scales that reshape galactic evolution. Already, proposals exist to harness intergalactic gas for hypothetical megastructures or interstellar travel projects that could inadvertently starve emerging civilizations of the raw materials their own stars would need. The Outer Space Treaty of 1967 prohibits national claims on celestial bodies, but no laws govern the diffuse matter between them, leaving ethics as our only compass. Yet restraint raises its own moral questions. If we discover a galaxy on the brink of collapse, its gas reserves depleted, its star formation halted, would intervention become a duty? Picture an advanced civilization spotting our Milky Way's impending collision with Andromeda and choosing whether to alter its trajectory. The same principles apply to our studies of intergalactic gas. Knowledge brings power, and power demands responsibility. Some argue that cosmic evolution should remain untouched, a natural process free from meddling. Others counter that intelligence itself may be the universe's way of achieving self-awareness, granting us stewardship over its fate. The heart of this debate lies in perspective. On cosmological timescales, our civilization is a flicker, yet our decisions could echo eternally. Intergalactic gas isn't just fuel or data. It's the connective tissue of the universe, the medium through which galaxies communicate and evolve. To treat it merely as a resource risks repeating Earth's environmental mistakes on a galactic scale. But to ignore its potential might deny future civilizations the tools to survive cosmic threats, asteroid impacts, nearby supernova, or the eventual heat death of the universe. Perhaps the answer lies in humility. Just as indigenous cultures often understand ecosystems through reciprocal relationships rather than domination, our approach to cosmic exploration could emphasize harmony over control. Instead of extracting, we might learn to listen, studying gas flows not to manipulate them, but to decipher their ancient rhythms. In doing so, we wouldn't just preserve the universe's integrity, we'd redefine progress itself, measuring our advancement not by what we take, but by what we leave undisturbed. The greatest discovery may not be how to harness intergalactic gas, but how to coexist with it, a testament to wisdom written not in stars, but in the spaces between them. From the primordial gas of the Big Bang to the intricate cosmic web of today, intergalactic gas is the unsung hero of cosmic evolution, silently shaping galaxies, fueling stars, and weaving the very fabric of reality itself. Think of it as the universe's original storyteller, encoding its history in atoms scattered across the void. Every wisp of hydrogen, every trace of oxygen drifting between galaxies carries echoes of supernova that exploded before Earth existed, of quasars that flared to life when the cosmos was young. This gas isn't just a backdrop, it's the stage upon which the drama of cosmic evolution unfolds, the invisible hand guiding the birth and death of stars, the rise and fall of galaxies. Yet for all its grandeur, the story is far from finished. Telescopes like the upcoming James Webb Space Telescope and the European Space Agency's Athena are poised to peel back even more layers of this hidden realm, revealing how gas flows shape the universe in real time. Imagine watching a galaxy's first breath as it draws in gas from the cosmic web, or tracing the path of heavy elements as they voyage from stellar explosions into the voids. These aren't just scientific curiosities, they're clues to our own origins. The iron in our blood, the oxygen in our lungs, all of it was forged in stars and scattered by the same intergalactic currents we're now learning to map. What's thrilling is how much we still don't know. Why do some gas clouds collapse into stars while others linger for billions of years? How do magnetic fields, too faint to detect directly, sculpt these invisible rivers? And could there be forms of matter or energy hidden in the gaps, waiting to rewrite the rules of physics? Each answer begets new questions, a reminder that the universe is always more complex, more mysterious than we imagine. This isn't just astronomy, it's a reflection of our place in the cosmos. We're made of the same atoms that drift between galaxies, bound by the same forces that weave the cosmic web. To study intergalactic gas is to trace our own lineage back to the dawn of time, to see the universe not as a static expanse but as a living, breathing entity, still growing, still changing. And as we stand on the brink of new discoveries, one truth becomes clear. The universe isn't just out there, it's in us, around us, whispering its secrets in the language of atoms and light. The next chapter of this story is ours to write. What will we uncover when we listen?